Thanks for joining this new session of the Victor short course. So today we're gonna talk about debris flows and Lahars, and we're gonna show you the Lahars model that we have on Victor with a short demonstration. So Sam is going to lead that session, and I'm going to be there. If there's any questions, please use the chat or raise your hand, and we'll be happy to answer answer them. So Sam.
Yep. All right, great. I will share my screen then. Can you see it right now?
Not yet.
Not yet.
Mm-mm.
Let's try that again. All right, let me restart real quick my browser.
Yep. Oh, you're muted.
There we go. Okay, of course it brought me in mute. Okay, great. So, as Sylvain said, today is focused on lahars and debris flows. What you see here are a couple different examples of actual debris flows. Sylvain, I'm not sure if you can say where these are or if you know where these are.
Yeah. So
Um,
the two upper images are from Indonesia. It's the lava that happened up after the 2010 eruption of Merapi volcano in Java. And then the bottom left is, I believe, Casitas in Nicaragua. Yeah, one of these lahars that happened. I remember, I think it was in the early 90s.
Great. Yeah, and then on the right you can see the one of the models. I think this is an older version of Laharsi than what we were using, but it does calculations and approximations of the total flow depth. Yeah, so just a quick background for lahars themselves. What often generates them are rainfall runoffs and then some type of slope failure or something like rapid snow or ice melting, uh, overflow from a crater lake, or at worst, a tectonic earthquake. But generally, it comes from a large amount of water or liquid in a very short amount of time. And it can be syneruptive or post-eruptive, but it generally occurs as a secondary flow originating from a pyroclastic flow or some type of debris avalanche or something like tephra as well. And then the kind of transport systems of these lahars are generally two-phase. There's the liquid fraction, which is the heavily water saturated flow, which you could kind of see more in that left side. It looks like kind of a dirty wave of water, but if we go back here, there are rock fragments in that as well, and larger solid fractions that can grow up to, or that can be up to several meters. And with these combined, it becomes a very destructive force due to the momentum of the solid fraction. And then, of course, if the water and the water saturated flow or the liquid fraction is high enough, that can also do a lot of damage in its own right. And what this system does is it allows it to flow over gentle gradients, and it can flow very far away from the source and inundate those areas. So there's mainly three types. For now, we won't show the movies, but there's debris flows, which are at least 50% settlement and are quite dense. There's the transitional flows or hyperconcentrated, which are slightly less dense and slightly less sediment, and then muddy stream flows, which are, as it says, mostly streams, more liquid. Yeah, so here are two examples like you saw on the right that you were close, Sylvan. It says it's November 1985, so this is Colombia. And you can see that there's a volume of about 4 times 10 to the 7 meters here, and it reached over 100 kilometers away from the initial eruption or initial debris flow point. And we've gotten much better, but at predicting and kind of emergency communication. But you can see that the impact of a debris flow like this killed more than 20,000 or 23,000 people. And then on the left side, you can also see what's left over basically from the debris flow. It flattens everything it touches in, tens or even hundreds of kilometers away. So generally, debris flows are, what would that be? 1,000 to 100,000 cubic meters, but the largest debris flows can be upwards of tens of millions of cubic meters. So you can see here, these are mud flows from Mount Rainier, and the total inundated area was 350 kilometers, and you can see it reached almost 150 kilometers on the run out. And at the worst point, it was up to 200 meters thick. So they really are like a force to be reckoned with. We'll talk a little bit about the actual flow transport and the the physics behind that, but we'll also have slides and references for you to look into more. So there tends to be a lot of bulking, which is the erosion and incorporation of secondary debris from lahars as they move and grow downstream. And there's so we can skip the bulking factor for now, but there's also the inverse of debulking, where the lahars start to deposit certain particles due to their size or density as it moves downstream. And this differs from the general deposition of the sediment because it usually removes larger or dense particles from the flow. So just here's kind of a visual representation. You can see the actual sediment discharge on the bottom in a few different examples, or a few different heights of the actual liquid fraction, and different examples of it being settling or being discharged. And yeah, I don't know, Sylvan, do you have any particular insights to the transport and deposition?
Just to show you that the deposits usually aggregate with time. It's not something that's gonna all freeze at the same time and create one unit. So it's generally aggregate with time. So the first thing that arrives at one particular point is the water, right? And so there's a time lag between the water arrival times and then the sediment arrival time. And the more you go downstream the volcano, the more this time lag is going to get bigger and bigger, right? And so you can see that on the graphs. So the peak of water discharge is going to come first, and then the peak of sediment discharge is going to arrive much later on. And this little sketch are showing you like example of stratigraphic section that you can get from the deposits, and you can see that you can get reverse grading or normal grading based on how much sediments are gonna be deposited based on this bulking and debulking effect. So just to show you that it's a little bit, it's a complex transport and deposition mechanism that sometimes it's tricky to actually put that into numerical models.
It also does go to show how destructive they can be because of the uh, kind of delayed nature of having the peak water or liquid discharge and the sediment discharge and kind of evolution happen at different times. Impacts the same area twice in two different ways. I think most of this we can skip for now. Depending on the type of flow, there's cohesive flows that will have more clay, or non-cohesive flows that have a smaller amount of clay, but this can change the overall mobility of the actual overall debris flow. But as you can see, there's small changes that can produce, or small changes in the volume percent of the actual sediment can change the rheology of the overall debris flow significantly. All right, so some modeling constraints that often come up and are often simplified for different types of models. So because these are fundamentally, multi-phase flows, um, they're mostly have nonlinear behavior and different and increasing strain rates. There's well, so there's kind of four principal components that are often implemented in the Lahar models or the debris flow models, and it's some set of terms that describe the conservation of mass, and if they're heavier or more complex, they'll also describe the conservation of momentum of the bulk flow and its components. They give a description of the channel geometry in one way or another. This could be through a DEM or other elevation data. Some way to quantify the flow resistance, and then finally, some way to actually numerically solve the PDEs. In the case of Lahars, which I'll talk about in a moment, it uses a more simplified concept called like the H over L cone or like the energy cone. So this is for a more complex model that will often take much longer to run. So again, there are different types of simulations or models we can do. There's the empirical models based on the observed correlations, but they don't really have the flow physics. There are simplified rheological models which use some kind of consistent stress strain rate, and then don't worry about the composition as much. Then there's models that go towards the hydrological side. They focus more on the liquid phase or liquid portion that assume more Newtonian behavior, but can be calibrated to Lahars debris flows a bit more through the modification of the flow resistance. And then we're getting towards kind of more sophisticated versions where they try to describe the constitutive behavior of the multi-phase, and then finally there are mass flow models that combine the two, that actually have that deposition of sediment and entrainment, or the some type of stratification of the actual grain size. But so as it says right here at the bottom, the differences come down to how the models work with the flow resistance, because these can be multi-phase, and how faithful they are to the underlying physics. And of course, as we've seen throughout the course, this is a compromise between computational tractability and then actual mathematical accuracy. And sometimes, like in the case of Lahars, we might just want a high volume of examples over a wide, random range, rather than one highly accurate or highly mathematically accurate example. So this is an older version that used. I'm not sure, Sylvan. Do you remember what like programming languages and setup this originally used?
At the very beginning, I think it was using its own like I don't remember exactly, but before it went into ArcGIS, I think it was just using some Visual Basic stuff like
Mm.
it was its own interface.
Yeah. So, what I'll go to in a moment, and or in 5-10 minutes, is this newer version that was made by Keith Blair. He is, I think, a software engineer by trade, but he ported this all to Python. It has a GUI. It's quite nice, and we'll get to that in a moment. But uh, the original Lahars was based on historical data. It was supposed to be rapid, objective, reproducible estimation of areas at risk, but it didn't really capture the flow dynamics properly. Um, I think for now we can skip this a bit. Um, Different ways of expressing flow resistance, whether it's the Bingham model, the Bagnall model, or some combination of the two. Um, but yeah, if you want to look into this more, I recommend reading the original papers or anything that uses or expands on something like a viscoplastic model, unless you have anything else to say, Sylvan.
No, it was just it was just a slide to show you like how complex we can go into the rheology of these flows, and the problem is that because they're so complex, then there's many different approaches that can be done. Whether you want to focus more on the shear stress and the yield strain using viscoplastic models, or whether you want to focus more on the particles into like collision or fusion forces, and then you can have a combination of these. So it's just showing you how complex you can go into this rheology, and in the end it's always going to be some approximations, right? So it's just a question of how much data do you have, and how much you want to use this data to actually try to refine your rheological model.
Yeah, absolutely. Um, same idea. We'll kind of continue through these fairly quickly, but these are the rheological models. This is focusing on the hydraulic flow. Do we want to treat it as a conservation shallow water equation, or do we want to use some type of Coulomb mixture model? This one has both kind of the fluid phase and the granular phase, which adds more realism, but also adds a lot more computation. Uh, there's also some flow transformation models that allow the density to vary a bit. But again, this is just one more kind of approach to a Lahars or a Lahar or some type of debris flow model. All right, Sylvan, I can keep my screen up, or if you want to share it and go through the case study, and then we can come back to me and I can start talking about Laharzian Victor.
Okay. Yeah, very quickly. Well, we can keep your presentation, and I can tell you to like move
Okay.
from side to yeah. So very quickly, this is just a case study that I've been working on during the past few years. It's 2005 Panabash debris flow in Guatemala, which occur at Volcan Toliman, which is one of these volcanoes that is in the lake Atitlan caldera around it. And so these debris flows occur in 2005 during the passage of tropical storm Stan um, between the October 2nd and October 6th. So it was very heavy rainfall. This volcano is a dormant volcano. It's not active, and you can see on the three-dimensional model on the right side that you can see the initiation of this debris flow pretty high on the slope of the volcano, and this debris flow used some previous channels that were used by previous debris flows at this volcano, and went down all the way to the lake Atitlan. And between the lake Atitlan and this volcano, there is a town called Panabas that was unfortunately buried and destroyed by these debris flows. So there was about 400 people that were killed. So these are pictures of some of the damage and impact of these debris flows on the channel and on the alluvial plain where the town of Panabash is located. But also you can see here at the bottom the impact left by the water above the on the top part of the flow, basically showing you how we can estimate, for example, the solid fraction inside a lahar by just looking at the depths of this water splash on this. I believe there was an hospital, and then the depths of the thickness of the deposit that are below. You can do a ratio of this and try to get the volume fraction of solid. You got to be careful a little bit because the splash is going to create a momentum. So that would be like a maximum value for the or a minimum value for the solid fraction and maximum value for the fluid fraction. But if you have other locations where you can try to calibrate this ratio, then it's even better. And then on the bottom right is just showing you that this debris flow was one out of many debris flows that came down this area. And so there was many previous events that produce mostly hyper-concentrated flows where the deposits are really thin, just a few centimeters thickness. But there is a record of multiple debris flows that occur in the last 100 years in this area. So there was some field mapping conducted by some colleagues in 2006, just after the event. So they were able to map the deposits from the two channels, the eastern channel and western channel. They were able to estimate volume fraction of water up to 40% volume fraction of water, and they were able also to estimate the total volume of this flow and the distribution of thickness as well. Yeah, next. And what we needed actually was an up-to-date DEM. So we managed to get a DEM of 10 meters spatial resolution made from IGN topo data, but the DEM was not really good at reproducing the channels, especially the narrow channels where the debris flow, the 2005 debris flows came down. So we had to adjust the DEM and recreate the two channels using some high resolution auto photos. And that's the DEM before and after. Yeah, as you can see, the two channels are much better defined there. Yeah, next. So we first tried to run some Lahars PY modeling and simulations, and what we did was trying to use some pre-existing coefficients that are used for debris flows. So Sam is going to show you that later on, but there is some coefficient that you can use based on the type of lahar you're considering. Remember, there's three types of lahar: debris flows, hyper-concentrated, and muddy stream flows. So based on this type of lahar, you can have different planimetric coefficient and cross-sectional coefficient A and B that you can use. So you can see the results using debris flow coefficient on the left and hyper-concentrated flow coefficient on the right. And you can see the big difference in the runout, especially for the western flow that goes much further all the way into the lake. So it all depends on whether you want to focus only on the debris flow part, or you want to also try to model the fluid portion of this lahar that can go, much further away than the debris flow portion only. So these were just some initial tests using Lahars. And then we use other models. So if you go next, we try to use Titan 2D and Volc Flow. So for that, we were using mostly a Coulomb rheology where we our internal friction angle, basal friction angle, the same as what we did for the PDC last week. But then, in addition, we're actually putting a solid volume fraction, and so the flow is actually able to be separated into a water phase and a solid phase. And then we use another model next that is called Flow2D. It's unfortunately not open source. You have to pay for a license for that, but it's using a rheology that is a little bit different than other models. It's using what we call a shear stress relationship, using a quadratic solution. So it's mostly a Bingham behavior. So you have a yield strength and then a viscosity, and it's adding like a turbulent dispersive term to it. So just a modified Bingham. And the good thing with this rheology that is also taking into account the roughness of the channel base, which was proven to be very critical during this simulation at Panamash. So basically, modifying the rheology based on whether your substrate is smooth or rough. So next. Okay. So these are some parameters, input parameters that we can use to simulate these flows. So you can see they go from area volume, solid volume, sediment volume concentration, H/L ratio, then all those other parameters. Next. And then we can try to calibrate the rheology used by Flow2D, for example. The same way we can try to calibrate the basal friction angle with Titan 2D. You can do that also. The cool thing with Flow2D that is actually using a direct relationship between the yield strength and the volume fraction of solid. So you can actually try to estimate that using a viscometer on some deposit sample that you have. And that's what we did here. We tried to use a calibrated value of the relationship between the yield strength and the viscosity and the volume fraction of solid. Try to see how much that impacts our simulations. Next. Yeah, I'm going to skip that. This is just to try to validate your model results. I think we're going to talk about that a little bit more when we're going to talk about benchmarking and other things. So we will have a code very soon on Victor that can allow you to quantitatively validate your model results against a solution, for example, or compare it against another model. So for that, we use these similarity metrics that are based on the footprint of your model against the footprint of map deposits, for example. And you can calculate, how much false negative, false positive you have, and try to get an idea in terms of like numbers of how your model is performing against some natural flows or deposits. Yeah, next. All right, these are some results. So you see that compared to the Lahars simulation that I'll show you now, we can start much higher on the flank of the volcano because we can actually use an hydrograph that's going to allow you to compute the discharge of water and sediments over time. So you put that as an input for this Flow2D model, and then you can see that you can compare the flow velocity and the flow thickness at different locations along the channel. And finally, you can actually try to compute these validation metrics and see how much the simulation is comparing to the map extent of the deposit. So here we got some better results using the calibrated viscosity or the calibrated rheology compared to the uncalibrated one. So this is just to show you one example, of Lahars simulation that you can do. So by combining different models, whether you want to use a purely empirical model like Lahars, or whether you want to go into the process of trying to calibrate your input parameters to get slightly better results. I would say it really depends on what type of data you have on the flows and how much accuracy do you want your models to be in the end, because you know, depending on your end goal, you may want to use a model that includes a bit more physics than another one. So I would say the choice of the model is pretty important. It is as important as the choice of the input parameters. Um, so right now on Victor, we have the Lahars model that Sam is going to show you now, and we also you also have the possibility to run some Lahars simulation using Titan 2D. I can show you that quickly after Sam is done, or you can also do that with IMAX. Um, Sam, if you want to start with Lahars, and then after that I can show you quickly the Titan 2D example.
Sure. Okay. So I'm gonna take another 2 minutes to discuss this, and then I will get everyone started on the kind of activity for today. Um, so right, so Lahars is an open source tool, but to model various flow hazards. So what we're gonna do in this case is we use a DEM, and Lahars creates a stream file, flow director to file, and an energy cone based on the H/L ratio, and that which from that creates a set of initiation points, and then the subsequent flows. And then what we'll do is we can take these outputs and put them into QGIS and get a very nice overall output. Yeah, so talked about this here. So I'll talk briefly and say, so the point where material accumulates can theoretically be determined as where the ground surface meets the line from the apex of the volcano. With this that angle you can see against the horizontal. So here's the apex of the volcano, here's the volcano slope, and here's the H/L line. And what this creates in 3 dimensions is a cone around the apex of the volcano, which is known as an energy cone. And what this does fundamentally is that, excuse me, the water, the liquid, will flow down the sides of the volcano, form streams, and when these streams intersect that energy cone line, Lahars have a high chance to initiate, and these will be the initiation points. So you can see this one example of different streams and initiation points in that energy cone.
Yeah, can I add something?
Yes, please.
Yeah. So this is just showing you how different these initiation points are compared to the model I was showing you before, like Flow 2D, for example, or Titan 2D, or IMAX, that's going to be able to compute the transport and the erosion, right, of these flows. Lahars is not doing that. It's only computing the deposition. So that's why you want to start very low on the flank of the volcano, right? Because you want to start on at a point where it starts depositing all these blocks and ash, right? So you don't want to start too high on the flank, because the model is not able to actually model the transportation or the erosion due to these flows. So it's a big difference, and you need to take that into account when you're choosing the source location for the Lahars model compared to a depth average model, for example. That's going to be different.
Absolutely. Let's see, volume material. Yeah, so there's a couple more things we can talk about with the volume of material mobilized, and like cross-sectional area and the planimetric area of the flow. But again, this is all in the Lahars models folder. It's on the GitHub, so if you want to read into it more, it's all there. So now what I'd like everyone to do is, if you go into your shared the folder for week 7, there is, you can see there's the example in the lab. Today we're just going to start with the example. So if you can open up Victor, open up the first example, and then start following the instructions. I mean, I can do this along with everyone, Sylvan, or what? It depends what you think the best kind of course of action is.
Up to you. I mean, if you want to do it as well, that's fine. Otherwise, we can also um, let them do it and then see what they get.
Sure. Um I would say everyone start working and I'll show you. I don't have the Mount Rainier or Rainier example, but I do have something else that I can show quickly. Sometimes uh the desktop needs a second. But yeah, if we have a Padlet of some kind for the final output, that would be great, just so people can share. The long story short is what you'll be doing here is creating the initiation points and running the flow model. So in the end, you should see something like this. And what we're using is we're taking the outputs, putting them into QGIS, and then cleaning up the topography, making changing the color ramp or the color profile for the flows to make them stand out more. And then you can see here's our final example with some very good examples of different Lahars based on the initial points and energy cone that we specified. Let me open QGIS just as an example. Yeah, so if I just open a couple of these for an example real quick. And then let's also add the actual all right. A little hard to see here, but this is using a different DM, but if we go through all the flows and we can set this to hold on, let me look at this real quick. If I hide this, these actually might not have any data. Let me clear all this. Okay, that's a much better example. So we can, possible this might be shifted, but this is definitely a much better example of what your output could look like. And what we can do here is change to actually, maybe I should follow my own instructions here. They're actually very well done. Yeah, so if you have any questions, just let us know in the chat. And then also what the let me find, yeah, so yeah, this is Lahars. Everything should be in the example folder, or you can start in the example folder for now. That's probably the best place to put your files. And it's basically just these couple of buttons and fields that you need to fill out. A lot of these should be able to stay the same, at least the numerical values. You're going to change the stream files of and or like the name of the files to correspond with your DEM, and change the apex and the Chaparral ratio possibly, but in the end you'll get a nice set of initiation points. And then once you create them, you can go to create flow outputs. It should fill some things in automatically. You put in the volumes you want and create flows, and then it will just spit them right out into I think you can actually specify, yeah, so the flow output directory, you can just specify directory inside that example folder, or whatever subfolder you pick, and all your outputs will be right here. And you can see it shows the naming is actually very helpful. So it's the initiation point 4, and then I think V1 versus this is different volumes. So it's 1 times 10 to the 5th, 5 times 10 to the 5th, and so on. So it has all these different initiation points and volumes neatly named. I don't know, Sylvan, do you want to take over? Do you want to specify anything?
Just wanted to add here that you can select, different volumes, so you can basically do several simulations at once, which is pretty cool. So it's not limited to only one simulation, right? One flow in one channel, but you can actually say you want several volumes, and then several initiation points, and then you can run this all and then get that map with 10, 20 Lahars simulation at once. So still not completely probabilistic, but I would say scenario based, which is pretty cool. And it's super fast, right? It runs in just a
couple of
few
seconds.
right? Yeah, so that's really good. I think that's what the main advantage of using a statistical model like Lahars is that you can really the setup for the simulations are pretty quick, especially now that we have this new way of using the energy cone to actually set up the initiation points around the volcano. And then once you got your initiation points, then you just have to select the volumes, and then it's going to compute the cross-sectional area and the planimetric area of your flows. So it's a pretty good tool if you want to get the first approximation of how far Lahars can go around a volcano, based on some scenarios that you define based on the data you have from previous Lahars.
Yeah. And one pattern you probably have started to see is the kind of trade-off between statistical modeling and then having something that's depth averaged or can deal with multiple phases or different or like differing rheologies or there's lots of different kind of levels of complexity. And what we do a lot in the hour we have for the course is these shorter statistical models, and then we give you for homework to work on with the models that take longer. But it's an important trade-off to think about and discuss, which is, do we want a lot of runs, a lot of data that is possibly accurate or has kind of a large range of accuracy, or do we want a few runs that will be um, much more precise, but don't cover the full range of possibility?
Yeah, exactly. Yeah.
Uh,
And the cool thing is that,
um,
with Victor, we have these different types of models for you to try. And so, you can try Lardid and see how much you think Lardid is more applicable for your case study. And then you can also try other models that are more complicated, like Titan or IMAX. Yeah, let me share my screen quickly.
yeah, sure, take it.
So, go back here. All right. Yeah, so what you can do is with Titan 2D is change the rheology to model Lahars. So if we go directly to the cell number 6, you can see here that you have the material model. And remember how we choose the Coulomb last time model. Now you can type two-phase Pitman and Le rheology by just copy and paste that here into the model name. Then you can leave the friction angle like that, or you can change the basal friction angle. Be careful because this rheology is actually using the friction angles, but also it's using a solid fraction. So because we have water included into the model now, water is going to flow on very gentle slope, right? So if you don't want to get simulation that are going to go very far away, I suggest to still keep a basal friction um, pretty high. That's for the solid material, right? So you want to keep that basal friction angle to pretty high values to prevent the solid material to reach very very long distance. So you can leave everything the same, and then you're gonna go into the cell number 7 here, add pile, and then at the very end here, you have that option here. If using the Pitman and Loeb, please enter the volume fraction. So you can actually enter your volume fraction here as a value between 0 and 1, because this is a volume fraction of solid. Okay. So, for example, here I put about 30%. Because I was using, I wanted to model a hyper concentrated flow, but you can use anything between 0 and 1 here, and then you can run your simulation. You can leave it the same. Well, what I did here, I was using the same initiation location as the PDC, which I found it was actually it was too high. You will see because the slopes are very very steep at the on Merapi volcano, and so I can show you what I was getting in the end. Yeah, I was getting a Lahar that is going out of my DEM boundary, and I think I was getting velocities that are like about 50 meters per second in this location here, which is way too high for a Lahar, and that's because I forgot to change the location of the initial pile, right? So make sure you actually choosing some location that makes sense, that are based on the HOR cone or any other method that you want to use. So but you can see here how that actually changing the whole overall behavior of the flow compared to the PDC simulation we were doing last week, and that here, the flow is getting out of the DM boundary, so it's much more mobile. But I think this is mostly in part because my source location is way too high on the volcano flank. So again, make sure that your initiation points are correct to model Lahars compared to any other type of flow like a lava flow or a parasitic density current. But otherwise, that's all you have to do to actually run Titan to the to simulate a Lahar. And for IMAX, it's a little bit similar. I haven't tried it yet, but you can also just change the rheology. Each rheological law has a different number, so you can choose the rheology for Lahar, and I think just change the initiation point, and you should be able to get the simulation running. Okay, I don't see any questions in the chat. Do we have results yet? Not yet. Okay, no problem. We can actually let the week pass to see if some people manage to get some results from the Montrenier example. Is there something different, Sam, for them to do? I remember you had like an example and then a lab.
Yes, there's a well, the lab is a bit more focused on actually no, the lab is probably the best thing to do. They can also do I would say do the lab, but replace Mount Rainier with their own volcano or their own location.
Okay. Yeah, using it. So the lab is actually just choosing another DEM.
Mm-hmm. You can get the DEM from using the Victor dot get DEM function, like we talked about a couple of weeks ago.
Yep. Is there any questions before we stop that session? Comments, suggestion? I see on the Padlet that some of you did some PDC simulation already. So that's great. That's really cool. And so, yeah, I think your main job for next week is to go through the example for Lahars and try to do the same and post your results on the Padlet. Do either that on Montrenier or any DEM that you wanna use for your own case study, and then we can look at the results. I'm saying next week. Sorry, yeah, I forgot to say. There's no session next week. It's spring break here, so we're actually gonna meet in 2 weeks. I'm gonna send an email to everybody about that. But next meeting will be actually in 2 weeks. 2 weeks time. So you got a lot of time to upload your results and populate the Padlet. And again, if you have any questions, comments, please put them in the Slack channel or emails, whatever it's easier for you.